were talking about, I guess before I start, so I guess you guys got the email, so I just posted the next homework. You can now see it. Start and get started on it early. By the way, I'm sorry about all the computation that time. That last time. I really feel like you have to do that once to appreciate what computers are doing for you. And I know that now if someone just gives you a random module and they ask you to resolve it, yeah. So now you realize that computers are a very good way to do free resolutions and Hilbert series and things like this. But I really wanted you to know what computers are doing behind the scenes, and they're basically doing these long computations that you had to do. Okay. Okay. So we were talking about Hilbert series, right? And I told you that this is a very nice application of free resolutions. So let me just remind you that the setup that we're talking about is like this. First of all, we're starting with the polynomial ring in n variables, right? And we said that this is an n to the n graded module where we cut it up into pieces where each piece corresponds to the terms involving a certain monomial, x1 to the a1, x2 to the a2, up to xn to the an. Okay? And then I said that a module was multi-graded or n to the n graded or finely graded if you can decompose it as a sum of as a direct sum of submodules m sub a, where a ranges over n to the n, where remember that the condition is that if you multiply a monomial of multi-degree a with a monomial of, sorry, if you multiply an element of multi-degree a by an element, no, it doesn't work, right? I told you that didn't work. If you take a ring element, right, of multi-degree a, and you multiply it by a module element of multi-degree b, then you should get a module element of multi-degree a plus b. Right? So that's what it meant to be a finely graded module. And then we define the Hilbert function and the Hilbert series to just be the dimension of each one of the pieces. Right? And so I wanted to start today just by doing an example of this. So what if the module is the ring itself? Okay. I mean, I wrote this definition, and several of you looked at me and were wondering why this isn't just 1. And well, in the case that we most care about, that is 1. Okay. So what's the point? That if the module is the ring itself, then what is m sub a? Well, these are the polynomials, the homogeneous polynomials of multi-degree a. And so really there's not a lot of choices there. It's just x to the a, and all you get to choose is what constant you put in front of it. So this is just the things of the form c times x to the a, where c is a field element. By the way, remember that I told you I was going to use this notation where if I write the x 3 times and make it fatter, that's a vector. It's supposed to be like boldface font. Okay. And so the point is that this is just a vector space of degree 1. You just choose what c is. Okay? And so that means that this is just 1 for all a. And that's why you guys were wondering why. I mean, so you asked me why this is not just 1, and it is true that if the module that we're talking about is the ring, the polynomial ring, then this is 1. Okay? For all a. Okay? And so that's the Hilbert function, and now let's compute the Hilbert series. Okay? So how do we do that? The Hilbert series looks like this. summation over n to the n of, this is just 1. Right? So it's just 1 x to the a. Okay. In other words, I'm kind of taking every single monomial of every single multi-degree and adding them all. And I'm asking you to compute this. That might seem like a very big task because you have to do this I mean, remember, x is a vector here, x1 up to xn. Right? And a is also a vector. And when I write x to the a, I mean x1 to the a1 up to xn to the an. Okay. So how do I do this? Well, I claim that this is just equal to this. Very simple. Okay. This is a big function in n variables, but it's just equal to this. Okay. So let me justify to you why this is true. So proof. What is this 1 over 1 minus x? Let me rewrite this as 1 over 1 minus x1 up to 1 over 1 minus xn. Okay. So 1 over 1 minus x1 is just 1 plus x1 plus x1 squared plus x1 cubed, etc. Right? Then the next term is 1 plus x2 plus x2 squared, etc. And you multiply all of these guys up until 1 plus xn squared, xn cubed, etc. This is a multiplication, okay? You're supposed to multiply all of these guys. So what happens when you do this? Well, it's this massive foil, as they like to call it around here. So what do, right? You just sum all the possible ways of multiplying something here by something here by something here by something here by something here. So for example, one possible term that is going to come out of here is when you multiply all the ones, you're going to get 1. Right? But you're also going to get x1 times all the ones, so that's x1. Then if I want to get x1 squared, x2, x3 cubed, then you choose the x1 squared here, the x2 here, and the whatever I said, x3 cubed here. The point is that every single monomial is going to arise in exactly one way by saying, well, I need to choose the x1 to the a1 here, x2 to the a2 here, etc. So this is just, when you do this, this is summation of x1 to the a1 up to xn to the an, where you have total choice of what the AIs are. Okay, so in other words, the vector A is just any vector of natural numbers. Okay? So that's actually very simple. I mean, it's a very simple formula. Okay. Do you guys have any questions about this formula? So maybe let's call this H of R to remember that this is the ring that we're talking about. Okay. Now this is kind of interesting because if you remember, I mean I just gave you a proof of the formula for the fine Hilbert series, and it's this product. But if you remember what the coarse Hilbert series was for this guy, I mean, this guy also had a different grading where it was just a simpler grading by simple degree instead of by multi-degree. And remember that we got a formula for that guy, and we proved that it was just 1 over 1 minus x to the n. And these formulas look very similar to each other, right? In fact, you can see that if you were to plug in all the x's all the xi's to be equal to x, then you would get the old formula. Well, this is no coincidence. This is this is a fact that you can always do. So what is it that I want to say here? What I want to say is this. Let's say that you have a finely graded module like this. Okay? Then what I claim is that if you have a fine grading, then you also have a coarse grading. Right? If you can be graded by multi-degree, then you can also be graded by degree. And then from the fine Hilbert series, you can go to the coarse Hilbert series very easily. So let me just write this out. So if m is equal to this, right, then I can also decompose it like this. Let's say m equals 0 to infinity of m sub m, where basically, I mean, these are things of multi-degree A, and so what I'm going to put in my mth term is basically collect everything that has total degree m, right? So here, what I mean is that m sub m is collecting all the terms of multi-degree A such that the degree of that term is m. So I need that A1 plus up to AN is equal to m. Okay? And you can prove very easily that if this really was a fine grading, I mean, it needs to satisfy the property of a grading, right? But if this is a grading, then this is also a grading. Then this is a coarse grading. Okay. And it is a fact that if I want this, which the letter I'm using here is not bold, so that I mean that this is the coarse Hilbert series where I only pay attention to degree. So this is coarse. Then all I have to do is take the other one, okay? And let me, just to clarify the notation a little bit, I should remind you that I wrote here h of m and x. But this x is supposed to be a vector, right? It's a vector of x1 up to xn. So you can also think of it like this. Okay? You have n variables here. And what I'm claiming is that if you just plug in x into all the different variables, then you're going to go from the fine grading to the coarse grading. So this is the coarse Hilbert series, and this is the fine Hilbert series. So this is a nice general fact, and I told you when I proved that the regular Hilbert series of the polynomial ring was 1 over 1 minus x to the n, I gave you one proof, and I told you that I could give you another proof later. And here's the other proof, right? If you use this fact, then given that the coarse Hilbert series for the ring is this one, then the way that you obtain the fine Hilbert series is by putting in x for each one of the xi's. And so what you're going to get is 1 over 1 minus x to the n. Now, this is something which it's one of these proofs that is not very enlightening, and I think if I do it in front of you, you might just get confused by my notation, and it's not so enlightening. And I think that it would be more helpful actually for you to practice with these generating functions and just sit down and write a proof. And it's not a difficult proof, so I really recommend that you do this. So I'll leave this to you as an exercise. It's not a difficult exercise. It really isn't. Okay. So I don't know. Can you give me another example of a multi-graded module? Can you think of anything? Right, so last time we talked about how you could allow yourself to kind of give your ring an artificial grading because maybe you want to. By the way, you'll see today why we want to do that. But you can do that here. So for example, you can take the module given by the same polynomial ring except that you give it a fake grading by shifting it up or down by a certain vector. Maybe we'll call this minus b. Okay? And this is the polynomial ring. With degree shift b. And what I mean by this is that we're going to decree that the degree in M of the monomial x to the a is not x to the a, it's x to the a plus b. Well, sorry. When we say degree, I mean the vector, right? So the multi-degree of this thing is going to be a plus b. And so it's kind of the real degree plus a shift. Okay? So what's the Hilbert series of this guy? Well, first of all, do you remember when we did this in the coarsely graded case, right? In just the easier grading case, do you remember what happened when we shift the grading by a number n, by a number, I don't know, k, d, we used d. Right? So when we shifted the degree by d, something very, very simple happened to the Hilbert series, which is that well, you can look back and you see that we just multiply the Hilbert series by x to the d. And that kind of corresponds to saying, well, you just shifted everything up by d, right? So now you don't see anything in degree, you don't start in degree 0 now, you start in degree d. And the way that you would do that to a Taylor series is just multiply by x to the d. Here's the same thing. Now we're shifting all the degree by b. That means that we're not going to see anything starting in degree 0. We're going to start seeing everything in degree b. And so we're going to get the same old Hilbert series, except now it's going to be shifted by x to the b. Everything else looks the same. So that's pretty easy to compute. Okay. Okay. Now, let's do maybe another example, a very concrete example. I don't know, let's say that example. Let's say that we just do this for n equals 2. Okay? And we consider r of minus, I don't know. We're going to consider the direct sum of two modules where maybe the first one will be shifted by degree 0, 1. And the other one will be shifted by degree 1, 0. Okay? So what do elements of this module look like? Well, this is a direct sum of two guys. And so you can think of it as just a vector, okay? Where you take an element and it looks like this, where M1 is in the first guy and M2 is in the second guy. So, for example, what is the let's talk about this guy. What is M sub 1, 1? Okay. So what am I supposed to do here? I'm supposed to say what are the elements of this module that are pure of degree 1, 1. So can you tell me one element that has degree 1, 1 here? You see that the reason I want to do this example with small numbers and concrete degrees is that I want you to kind of pierce through this notation and see what this actually means. Maybe let me start with a different question, which is, I don't know, what is the degree of let me start by asking even this. What is the degree of this vector? The multi-degree of this guy. So this is the polynomial that is, this is the vector where the polynomial on top is just a very simple polynomial, it's the constant 1, and here it's 0. So what would you say that thing, what would you say it would be the degree of that thing? Any guesses? 0? So why 0? So, well, I think I see why, because it should be 0 because constants have degree 0. But then you have to take into account the degree shift. So this guy lives in a world where your degree gets shifted by 0, 1. Okay? So this guy should be of degree 0, but because it lives in this ring where your degree gets shifted up by 1, by 0, 1, this thing is really of degree 0, 1. Let's do another example. So what's the multi-degree of something that is 0 on top, and maybe it's we're in two variables, right? So x squared y. Well, the answer, first of all, should be a vector, right? Because it's a multi-degree. So what is it? Again, I'll take any guesses, whether right or wrong, or... So, okay, well, I heard several answers, and one of them was right. So here, this guy looks like it should be of degree 2, 1. It's homogeneous of degree 2, 1, except that this guy lives in this ring where your degree gets shifted up by 1, 0. Right? And so that means that even though it really looks like degree 2, 1, because it lives where it lives, its degree is going to get shifted up by 1, 0, and it's going to look like this. Okay. So it's 3, 1. What about this one? The multi-degree of 1, 1. I mean, there's an issue here, which is that it looks like this looks like it's of degree 0. It looks like it's of degree 0, right? But this guy lives here where your degree gets shifted up by 0, 1. So really, this top term has degree 0, 1. And this bottom term has degree 1, 0. And that means that the degrees don't agree. And so what that means is that this guy, which looks perfectly homogeneous, is not homogeneous. Because the top component has degree 1, 0, and the bottom component has degree 0, 1. So this doesn't really make sense. This is not a homogeneous term, so it doesn't live in a single m sub something. Okay. So given that, can you tell me some things that live in m of 1, 1? So x0, does that live in 1, 1? X has multi-degree 1, 0, right? And because it lives in the first row, its degree gets shifted up by 0, 1, so it has degree 1, 1 in this ring. Okay. So that guy lives here. What else lives here? Can you, someone different, can you tell me something that, if I want total degree 1, 1, then what should I put here? I need y, right? Because I need to look like I have degree 0, 1, so that when I get shifted, I get degree 1, 1. Now, for example, xy is something that should not look homogeneous to you, but it is homogeneous here. Because it's the sum of this, and these guys have both degree 1, 1. Okay. And if you think about it for a little bit, you'll see that actually anything of degree 1, 1 has to be something like this plus something like this. In other words, this is just the span of x, 0 and 0, 1. Okay? And that means that in degree 1, 1, the Hilbert function is 2. And I wanted to do this example explicitly so that you could see that the Hilbert guy doesn't have to be 0 or 1, which it seemed like it might have to be. Okay. Okay. Now you realize that this is going to take practice, right? But at least I don't think I've said anything too complicated, but I have said things that require practice. But I didn't really say any words you didn't know or anything. Okay. So where am I going with this? I'll show you. I don't need this. Don't need this. Remember this formula. This is a good formula. So let me make a definition. So remember that I'm gonna insert a word here, so I'll leave space for it. So a free resolution of M is something that looks like this, right? Where the FIs are free modules. Okay, and I said that those are the modules, and then we have these maps that go like this: delta 1, delta 0, delta 2, etc. And we need this this property that it should be exact and it should be the UFS should be free modules, where the sequence is exact and the modules are free. Okay, but I want to add an adjective here, which is graded. So what makes a free resolution graded? Basically, if you can add a grading everywhere so that the grading is respected. So what do I mean by this? I mean that M should be a graded module, F0 should be a graded module, F1 should be a graded module. All of these guys should be graded. And so let me spell this out. So the modules are free. And now they need to be graded. And the last thing that I need, and the maps should preserve degree. And what I mean by that is that if you take something of degree 2 here, then when you apply the map to it, it should go to degree 2 here. Okay? And the maps delta I are degree preserving. Okay. And we need to do an example of this so you know what I mean. So we have our favorite example of a free resolution. We'll do it over here. So we had this free resolution that looked like this. This was the free resolution that we did in class, that you did in the homework. And this was the free resolution for the module. So here, let's see. Here R was the ring in 3 variables, the polynomial ring in 3 variables, and the module was R mod maximal ideal X generated by X, Y, and Z. So we did this very explicitly. We computed syzygies and more syzygies and more syzygies. And in the end, we found an exact sequence that looks like this. Let's see. So here the map was X, Y, Z. Here the map was multiplication by this matrix. Here the map was multiplication by this matrix. Okay. Okay. So let me ask you, is this free resolution graded? Let's go down the list. So a graded free resolution is supposed to be a sequence like this. The sequence is exact. Well, we did prove that this was an exact sequence because this was a free resolution. The modules are free. Well, these modules are free because it is a free resolution. The modules have to be graded. So are all those guys graded? R cubed, R. They are, right? And the maps are degree preserving. So are the maps degree preserving? It's going to be the catch in a lot of these. So somehow being graded, the most important thing is that. This is the new condition. Well, I'm being graded, of course. Okay. So these guys are graded, okay? But are these maps degree preserving? And let me give you an example. Let's take something of degree, and here I'm talking about just normal degree, not multi-degree, okay? So let's take something of degree 1 here, of degree 0. Let's make our life easy, okay? So what's something of degree 0? 2. Okay? That's a constant. It has degree 0. Where does 2 become here? It becomes a vector in R cubed, which looks like multiplying by this matrix, right? So you get 2z minus 2y, 2x. And that is homogeneous, but it has the wrong degree, right? That has degree 1. And we want this to be degree preserving, so that whatever had degree 0 stays of degree 0. So given that, can you guys think of a solution to that problem? Well, you shift, right? That's the whole reason why I keep talking about shifting, and you're wondering why on earth I want to do it. If I artificially decide that the degrees here are shifted up by 1, then that means that 2 is artificially going to have degree 1 here, which means that it's going to have the right degree over here. Okay. And so the point is that if you have a free resolution like this one that is not graded, then you might be able to make it graded by just moving the degrees a little bit. Okay? And that's what we're going to do here. So, for example, how should I shift my degree here? I mean, you see that the problem is that you kind of want to go from the right to the left, because if I just shift this guy, then that means that I will have fixed this arrow, but I still have to fix all the other ones. And I'm going to have to change the shifting of everything for this to work out. So let's let this be just the usual degree, right? We don't shift anything. So here, elements of here are just of the normal degree. Now, is this map degree preserving? This is, because you're just taking a quotient, and if you have, I mean, remember that yes, basically. Okay. What is the decomposition here? How does this guy decompose into graded modules? I mean, what are the graded pieces of this guy? Well, what are the things that live in M? Basically, it's just the constants, right? And everything of degree higher gets killed. Okay. And so what does this map do? It takes the constants to constants, and it takes everything else to 0. Okay? And that's why this thing is degree preserving. Because if you take an element of degree 3, then you take it to the 0 of degree 3. So this is degree preserving, because really the only interesting thing that happens is that constants stay constants. So that means that I don't need to shift the degree here. Okay. Now, is this map degree preserving? Well, this one is not, right? Because here I'm actually multiplying by x, by y, and by z. Okay. So for example, if I take something that looks like this, 1, 0, 0, this thing has degree 0 here. And when I multiply by x, y, z, it's going to become x, which has degree 1. And that's bad, because we don't want things of degree 0 to go to some things of degree 1. And so the way I'm going to fix that is I'm going to shift the degree up over here. Okay. I'm going to shift the degree up by 1. Okay. Okay. And so now I've solved this problem. Now this map is degree preserving, right? Because what this map does is that it raises your degree by 1. You always multiply by something of degree 1. And so by making this shift in degree, I will have solved that problem. What about this map? Well, this map also takes things and lifts the degree by 1. Because all of these things that you see here are of degree 1. For example, if you take an element like 1, 1, 1, which is homogeneous of degree 0 here. Where is that going to go to according to this map? Well, it's the multiplication by this guy, so that's, I don't know, y plus z, z minus x, and minus x minus y. Right? So things go to a degree higher, and so the way I solve that is by shifting the degree of this guy. But the degree of this guy is shifted already. This guy has degree 2. It looks like degree 1, but over here we shifted of degree 2. And so that means that this guy should be shifted by 2. So I solved that arrow. But then finally we saw that also in this arrow your degree goes up by 1, and you have to fix that by shifting over here. Okay. And now I have for myself a true graded free resolution. Okay. Everything has a grading, and these maps respect that grading. Okay. If you take something of degree 3, then it maps to degree 3 all throughout the sequence. Okay. So that's an example. It's an example of a graded free resolution. And why do we like these guys? Well, for the following very nice reason. Theorem. If let's say that we have a finite free resolution like this, and let's say that it's a graded one. If this is a graded free resolution, then the really nice thing about this is that you can know exactly what the size of M is by the sizes of all of these guys. By size, I mean Hilbert function or Hilbert series. So for example, if you want to know the Hilbert function of this guy, then all you have to do is take the Hilbert function of f0, subtract the Hilbert function of f1, add the Hilbert function of f2, etc. Okay. And if I want the Hilbert series, then all I have to do is the same thing. Hilbert series of f0 minus Hilbert series of f1 plus Hilbert series of f2, etc. And I want to convince you that this is a wonderful theorem, and the reason why this is a wonderful theorem is that, as you realized in the previous homework, it is a tricky question to ask you what the Hilbert function or the Hilbert series of an arbitrary module is. But this tells you that if you manage to resolve it, if you find a graded free resolution, then you reduce the question of finding the Hilbert series of an arbitrary module to computing it for free modules, but for free modules it's very easy. We did it already. Well, we basically did it. So I'll tell you what we haven't done yet. But that means that so we can compute these very easily. We can compute this very easily if we have a resolution. A graded free resolution. Okay. This is meant to say resolution, I guess. So, for example, what does this say? Just to see this in action, let's see what it does over there. This says that the Hilbert series of M is equal to the Hilbert series of the ring minus the Hilbert series of the ring shifted by 1 cubed plus the Hilbert series of the ring shifted by 2 cubed, and then minus Hilbert series of the ring shifted by minus 3. Right? That's what the theorem says. Okay. And so let's go ahead and compute the right-hand side. What I'm claiming is that this right-hand side is always going to be very easy to compute because this is all free. So the easiest term is this one, right? So we know what the Hilbert series of the ring is because we computed it. It's just 1 over 1 minus x to the number of variables, which in this case is 3. What's the next easiest to compute out of all these terms? The last one, right? Because this, again, is just the polynomial ring. We're just shifting the degree up by 3. And we saw that the effect of that is just multiplying by x cubed. Okay. Now, how do we deal with these middle guys? What is the Hilbert series of a direct sum? Well, maybe a little bit easier is what is the Hilbert function of the direct sum? I mean, that's what this is, right? R to the minus 1 cubed is R to the minus 1 plus R of minus 1 plus R of minus 1. So we need to know how to compute the Hilbert series of sums. And so what I'm saying is, okay, if you have something of degree I in R plus S, how did you generate that guy? Well, the thing is that this is a direct sum, right? And so if you are in R plus S, that means that you're something in R plus something in S. And if you're homogeneous of degree I, that means that your R part is homogeneous in R, and your S part is homogeneous in S. Okay? So what that means is that this is the number of basis elements that I need in R. This is the number of elements that I need in S. And when I put what generates R and what generates S together, I'm going to get what generates R plus S. Okay? So Hilbert functions behave nicely with respect to direct sum. And that means that Hilbert series also. So what does that mean? What do we have here? We have a direct sum of 3 rings. So we just need to add their Hilbert series. Okay? But these 3 rings are the same ring. Right? They're R of minus 1. So what I get is 3 times that guy. Okay? And what is the Hilbert series of R of minus 1? Well, it's R with degree shifted by 1, so that's just x to the 1 over 1 minus x cubed. And here, this is a direct sum of 3 copies of R of minus 2, so what I'm going to get is 3 copies of the Hilbert series, and R of minus 2 has Hilbert series x squared over 1 minus x cubed. So what I get in the end is 1 minus 3x plus 3x squared minus 3x cubed divided by 1 minus x cubed. You like that formula? Oh. This is 1, right? So you might be concerned for a second, but then when you think about what you're computing the Hilbert series of M. So what's M? Well, we said that M is just this pretty trivial thing that only has constants, and everything of degree higher doesn't exist. So it makes sense that in constant degree, you have one generator, and then This is 0x to the 1 plus 0x to the 2. Okay? Because there's nothing in degree 1, nothing in degree 2, nothing in degree 3, etc. So this computation makes sense. So this must be the hardest proof of the binomial theorem, right? It's basically what we did. We just proved the binomial theorem. And in your homework, you did it for n. We did it for 3. You did it for n. Because in your homework, what you had was, you had n choose 0, n choose 1, n choose 2, n choose 3. So if you mimic what we just did, you're going to get exactly a proof of the binomial theorem. So that's good when a true theorem has a true consequence, right? But I hope you see the point, which is that if you actually want to do this for m, for a concrete m, then once you have the Fourier solution, actually once I manage to, I mean, even this purple stuff doesn't matter, you see? Because all I need to know is how many copies of the ring and what are the grades. Yeah? What are the grade shifts? I never looked at the purple stuff to make this computation. So once I have what I call the Berry numbers, yeah, these exponents right here, and once I have the degree shifts, then the computation of the Hilbert series of m is immediate. You just, maybe it's a little bit messy, but you can do it. Okay? And that's what this theorem tells you, that if you know how to resolve modules, then you can compute their Hilbert series. And so that'll be the next item of business. Is basically we are going to prove this theorem, and then we're just going to discuss basically what's the general way of computing Hilbert series. Now, one thing that I would ask you is also, I mean, first of all, think about this. This is a moment where probably you got confused about the grading today, and it's very important that you don't get lost, because we will do a lot of this fine grading stuff. Okay, this is not something that you can avoid very easily in the rest of this class. So think about this fine grading and think about how it goes with all of this. And in particular, one thing that you might want to do is do the same computation that we did there with the fine grading. Okay, because this theorem is also true if instead of the coarse grading, I have the fine grading. So what I mean by that is that I could have done the exact same thing, and instead of computing the usual Hilbert series, I could have demanded more. I could have asked you for the complete Hilbert series, and you could have done the same computation with keeping track of the whole grading and not just of the degrees. Okay? So you should really look at this and carry it out and basically imitate this computation. And I think that if you do that, then all this notation will make sense. And I warn you that, I mean, you should know that in the homework you have to do this, basically. And so it's good if you practice it with a small example, and then the homework will be easy for you. All right.